So today I'd like to talk to you about a research and development project that we've been doing at AdaCore, looking at applying Spark and Ada to this platform called OpenUXAS. Or as I like to think about it, Spark and Ada Do Autonomy. Now this is a collaborative research project between AdaCore and AFRL, and we have Dr. Laura Humphrey in the audience who supported us at AFRL on this work. So before I dive in, I'll pause and answer this question: what is a tool company doing performing research and development? So actually, AdaCore has a very rich history of research and development. Throughout our life, many of our products have come out of research programs. So GNAT, our compiler, came out of a research effort initially. Spark came out of a research effort. QGen came out of a research effort. And SSI, which I talked to you yesterday, is something that we currently consider to be a research effort. So at AdaCore, one of the ways we use research and development is to accelerate the development of new tools, like SSI and like QGen. The other reason we use research and development is so that we can put together use cases and examples that we can share with the community to illustrate how our tools work. And that's really what we're talking about here with our work on OpenUXAS. So what is OpenUXAS? OpenUXAS is an open research platform that was developed at AFRL. And this platform has the aim of supporting cooperative autonomy for autonomous vehicles. So if we look at current UAV operations, there's a mismatch between the original problem of having unmanned, purpose of having unmanned assets and the reality today. So the initial hope in having unmanned assets is that we would be able to use these as a kind of force multiplier, so that one person would be able to oversee multiple assets in the field. But the reality is actually very different from that. Most of the vehicles we have today have limited autonomy, and so we end up having a pilot that's dedicated to operating the aircraft. We have a sensor operator who's dedicated to pointing the sensors at different targets of interest. We have somebody who's doing overall strategic management for the mission, and we have various people that are consuming the sensor data. So instead of having one person to multiple assets, we still have multiple people on one asset. So in order to move away from this, researchers have been looking at providing better user interfaces and more autonomy that would allow humans to play a much more strategic role. So one example of this could be play calling. So the human operator would determine what plays the aircraft would take on, and this would accomplish a mission. So this might look something like this. So an operator might start with some kind of a mission area and mark it up to indicate regions of interest, to indicate no-go zones, to indicate the overall boundary of the mission. Then based on this information, autonomy could consider the total set of assets available and could plan which asset is going to accomplish which part of the mission. So this is what OpenUXAS does. OpenUXAS takes tasks, which are pieces of a mission, and combines these together according to the rules of some process algebra that expresses relationships amongst the tasks, and assigns these to available assets. So I'll pause here and make a couple of points. So first, throughout this talk, when I say task, I will never be referring to an Ada task. I'm always going to be referring to a task as a piece of a mission to be planned. Second, although I've set this up in the context of a military program, the applications that are envisioned for OpenUXAS are not strictly military. The assets that we're talking about are intended to be engaged in surveillance missions. These tasks are surveillance tasks. So we can easily imagine civilian applications for these. For example, we could use these kinds of systems to do precision agriculture. We could use these kinds of systems to provide surveillance and support of disaster relief efforts. So not strictly a military setup. And finally, I consider this to be the user's view of OpenUXAS. So this is really why AFRL was interested in putting this platform together, so that they could build a community to do research into cooperative control. But the other way to look at OpenUXAS, I think of as more the developer's view. So this is what the system actually is, or how the system is actually built. So OpenUXAS is a service-oriented architecture. Services, shown in purple here, coordinate with each other over the underlying switching fabric, which is shown in blue, to assign tasks, shown in green, to vehicles. So this is really how OpenUXAS is built. Now, with that background in mind, AFRL came to us with a question. Can we show functional correctness of OpenUXAS? Functional correctness is important because these keep-out zones, in particular, may represent terrain, they may represent obstacles, they may represent mission no-go zones. So we could think of these in terms of privacy, for example. We might want to make sure that these aircraft aren't going to be flying over an area where we have privacy concerns or safety concerns. We might want to make sure they're not going to be pointing their sensors somewhere they shouldn't be pointing their sensors. So there's a clear need for functional correctness, also so that we can be sure when the human operator looks at the proposed path that the autonomy has come up with, the vehicle will actually follow it. So that's what we're looking at. We want to know that what the autonomy says it will do is what the autonomy actually will do for safety and security reasons. So if we look at the way OpenUXAS is built, if we consider these services and if we consider this underlying infrastructure, we might ask ourselves, which of these components are actually functionally critical? And the answer that we come up with is most of them. In fact, we could probably say it's likely to be all of them. Now we might follow up, okay, given that most of this functionality is critical functionality, how was this originally built? And the answer that we come up with is it was built in C++11. And I know what you guys are thinking. You're thinking, what? Critical code in C++11? So there was actually a really good reason that AFRL did this. Originally, when AFRL set out to put this platform together, they were very much considering it to be a research platform. And so they didn't have strong functional correctness objectives in mind. Second, AFRL knew that the controls community overall is very interested in implementing their algorithms in C++. Or to say that a little bit better, right now the controls community uses C++11 for most of its work in cooperative controls. And so AFRL wanted to be able to support the development of these kinds of tasks in C++11 to lower the barrier for entry to the community. To get the best community involvement, they wanted to choose the language that was the most familiar. So we essentially have as an objective to keep this C++11 around. Now, AdaCore came in and said, all right, if you're really interested in doing functional correctness, then a good way to approach this would be to consider rewriting some of these core services using Spark and using Ada. So this is the goal that we had in beginning this collaboration with AFRL, to rewrite some of these services in Spark and Ada. And in fact, we can push that goal further and say we'd really like to rewrite all of these core services in Spark and Ada. And we might want to take it further than that and rewrite all of this in Spark, minimizing the use of Ada. And I suppose really if we wanted to take it to the extreme, we would consider rewriting some of these tasks in Spark. But again, we have as a strong objective to continue to support C++11 in these tasks. So that was our goal. Now we've talked a little bit about Spark here, so I'm not going to go into too much detail about Spark, but I'll just summarize quickly what we feel like we're getting from Spark in our work on OpenUXAS. So first, just by using the language subset, you get features, because Spark's language subset removes some of the features of Ada that are most challenging to reason about. And that difficulty is not just for tools, it's also for humans. So when you stick to the Spark subset, it's easier to write clean code. On top of that, Spark provides flow analysis. For us, flow analysis isn't that interesting because most of these services exist within single packages. And so considerations about the way in which we're using global variables are less important to us. Absence of runtime exceptions, the silver level, however, this does matter to us. We would like to be sure that OpenUXAS is not suddenly going to stop providing service mid-mission because of some arithmetic overflow. So we do pay attention to absence of runtime exceptions. And of course, the proof of functional properties is exactly what we want to do here. We want to show functional correctness. That being said, we're not looking at full functional correctness because we know we'll have residual C++ code, and the cost-benefit ratio of getting to full functional correctness doesn't make sense for this application. So, from Spark, the solid foundation of stone, absent of runtime errors from silver, and the proofs of correctness at gold, And also, these contracts serve as really excellent documentation to explain what the code is doing, and in many cases, why the code works the way that it does. So we feel we get an extra benefit from putting these contracts into our code. So that's what we're doing with Spark. The step that we took initially in working with AFRL was to choose one of these services and to rebuild it using Spark with a little bit of Ada. And this service is called the Automation Request Validator. When OpenUXAS starts up, the first thing that it does is it feeds information into the system about things like the available vehicles that can participate in a mission, the keep out zones, and the keep in and the tasks. Also keep in zones, but tasks. So this is a subset of the total information that's fed in. So this configuration data is picked up by all of the services, including by the Automation Request Validator, and stored in internal state. Then, when it's time to plan a mission, a specific kind of message called an automation request is fed into the system. And what this message does is it says, I want to plan a mission that involves vehicles with these IDs, tasks with these IDs, keep out zones with these IDs, etc. And so the Automation Request Validator takes this message and it asks, are all of these vehicle IDs that I've been given valid? Are all of these keep out zones I've been given valid? Are all of these task IDs I've been given valid? And once it's checked to make sure that all of these IDs have previously been declared, then it feeds the message into the rest of the system and declares it to be valid. So that's what the Automation Request Validator does. Now, we picked this particular service because its safety property is so obvious. Or functional property is so obvious. What we care about here is that when the Automation Request Validator says, yes, all of these are valid, they in fact have been validated correctly. So we took this and we rebuilt it in Spark and Ada. And because we wanted to do a demonstration, we further rebuilt some of the core functionality that sits below it in Ada. So we rebuilt service space, which provides the messaging glue, and we rebuilt some of the infrastructure that gets us down to our underlying messaging layer, 0MQ, in Ada. To accomplish all of this, we had to do 4 things. So first, we had to update the message set itself to be in Ada. Originally, the message set was provided in Java, Python, and C++. AFRL did a lot of work to take the generator for this message set and to rewrite it so that it would emit Ada code. We worked with AFRL to complete this. It's a good thing it was automatically generated because this was 202 packages and 32,000 lines of code. Once that was complete, we needed to rebuild this infrastructure that we could use to construct our demo. And this was about 30 packages in Ada and 7,000 lines of code. Then we had to build an interface to link the full Ada code with the Spark code. And we had to formalize our properties so that we could complete our proofs. All told, this was 11 Spark packages, 1,800 lines of code. And the predicates, there were 10 predicates we came up with to express the functional properties, and these were about 80 lines of Spark. Through all of this effort, we had an additional goal, which was to keep the fundamental structure of the code as close to the original C++ as possible. The reason we did this is because we wanted to make sure that if there was any kind of error in the output of our Spark and Ada implementation, it would be easy for us to go back to the C++ and identify the source of that error. At the same time, this complicated the proof, and I'll speak a little bit more about that later. So first, let's take a look at this notion of an interface between Ada and Spark. These are both the same language, so you might wonder, why did we need to do this? And the answer is the message set made heavy use of pointers in C++. So this is a complex data model. There were a lot of pointers. These pointers were used for things like dynamic dispatch and to reduce copying. So every time we dealt with a message, what we were actually typically dealing with was some kind of an object graph, where the different items in this graph were linked together using pointers. When we re-implemented the message set in Ada, we maintained this use of pointers as access types. And again, for essentially the same reasons. We wanted to support dynamic dispatch. We wanted to reduce copying. But Spark didn't have pointer support when we started on this. It does now, but the pointer support in Spark now is also limited. So Spark pointers have to be non-aliasing, and Spark pointers can't be placed in tagged types. There's good reasons for these limitations. You can bug Yannick if you have questions. I'm sure he'd love to talk to you about it more. But for us, we had to find a way to get these object graphs linked together with access types into Spark. So the first thing we thought of is, well, we could simply deep copy these object graphs and replace all the pointers. But that's pretty clearly undesirable because it's greedy. You have to do this for the whole object graph, whether or not you use the whole thing. And it's very heavyweight. So we didn't like that idea. A second idea could be to use an adapter. So you could take this object graph and you could put it inside of another object, and then you could expose an interface that only reveals those pieces that you care about and translates them into a type that Spark would like. So that seems good, but it still feels a little bit heavyweight. But since this is Ada, we can do better. We can use a private type, and that's the approach that we took. So we say, for example, that a Spark object is private, and then in the private part of our package, we say what this actually is a renaming of object any, which is some class-wide access type to the object that we want to reference. Then we provide functions wrap and unwrap. We turn Spark mode off for this, so Spark is not allowed to call these functions, but the full Ada code can. And this provides the means to put one of these object any's into the Spark compatible type and to take it back out again. For Spark to use this, we provide a dereference function, and then we implement this dereference function in the private part by simply saying that it's x.all. So this takes the value out of the pointer and returns it to us. And we've managed to do this all in a way that is very lightweight and very inexpensive. And it's also lazy. We can introduce these things only as we need them. So rather than use a heavyweight adapter, we have a very lightweight interface that we've constructed between the Ada and the Spark. And we think this is a pretty good pattern for use when you have code in Ada that has pointer types that you need to exchange with Spark. So that's the interface we constructed. With that in mind, we've set about formalizing our requirements for the automation request validator and implementing it. So I'm not going to go into a ton of detail about how we did this. On this slide, what I'm trying to do is provide just a bird's eye view of what we did. So here on the left, we have the specification. On the right, we have the body. And in the specification, we have the properties that make up the functional contract for this automation request validator. So we want to be sure that when the validator says this message is valid, it has actually correctly checked that the vehicles, the keep out zones, the keep in zones, et cetera, were previously declared. So here we have a region of code where we look at operating regions, keep in zones, and keep out zones. And on the right, we have the implementation where we actually check this. And what the implementation does is it steps through and it looks at each one of these IDs and simply checks to see if it was previously placed into some map. And if it's not, then it raises some error message, and we want the error message to correspond to what actually went wrong. So there's a little bit of extra functionality that happens in the body, but overall this is a very close implementation of the spec. So we were able to prove that that was correct. And in fact, we were able to prove that all of the predicates that made up our functional contract were correct based on our implementation. And in the process of doing this, we found a bug in the original C++. So in order to complete this proof, we had to fix that bug first. So that's the work that we did on proving correctness. So this was our first step. We rewrote the automation request validator in Spark and a lot of underlying infrastructure in Ada so that we could put together a demo. And the way we did this demo is we took the original C++11 code and we turned off the automation request validator in its configuration file. We then kicked this off in its own process. So now you can configure OpenUXAS by sending in all the messages that identify your vehicles, your tasks, and your keep out zones. But when you feed the message in that should kick off a mission, there's nothing to handle that message. And so the system just waits. So then we take our Spark and our Ada implementation, and we kick that off in its own process. And now these two processes can talk to each other using the underlying messaging layer. So when we feed that automation request message in, the automation request validator that we implemented in Spark picks it up, validates it, and sends the validated message back into the system, which the C++11 code picks up and handles. And so the mission completes normally from that point forward. We chose to do these in 2 separate processes because this was the fastest, easiest integration we could do at this step. And we also liked the flexibility of being able to keep these in 2 separate processes. You could imagine, for example, using some platform like Ray talked about where you had strong partitioning and running the safety critical components of OpenUXAS in one of these safety critical partitions and leaving the C++11 code in some lower criticality partition because you trust it less, and still having this communication over the underlying message bus. We could, of course, have put this into one process, and that's something that we're working on right now to provide a better build for OpenUXAS that illustrates how to link together the Ada code and the C++ code directly so that they can exist in one process. So what's next? I mentioned that our goal is to do everything, but it's not realistic to think we're going to do that as our immediate next step. I also mentioned that the implementation that we have at present stuck as close to the C++ code as possible. And that really did cause some problems for us. So many of these functions in C++ were very, very long. They were essentially poorly modularized. And when we did the translation to Ada, we ended up with very long procedures. And long procedures are challenging for Spark. They provide too much state for the provers. The provers have a habit of getting lost in these cases. Better modularity of code always yields better results when you're doing static analysis with tools like CodePeer or proof with tools like Spark. The second problem that we had with this was that there was a lot of use of heavyweight formal containers to represent the state of the system. And the third problem we faced was this heavy use of pointers in the original message types. Even though we had this nice abstraction layer, that still provided more complexity for the provers to deal with. So what we've done is we've begun to work on refactoring this code so that we can accelerate and simplify our proofs. We've broken up the long procedures into smaller parts. We have replaced some of the heavier weight formal containers with lightweight functional containers. These containers do more copying, but they expose to the prover a much slimmer interface, which makes it much easier for the provers to reason about how these containers are working. And we've reduced our dependency on pointers. And in doing this, we've vastly accelerated the proof and we've vastly simplified our annotations. At this stage, we have only some very simple annotations for loop invariants, and all of the rest of the annotations that we previously needed were removed. So we're pretty excited about this as an illustration of how minor refactoring of your code can cause Spark to be much, much more effective. So that's it. I hope you follow our progress. Everything that I've talked about today is completely open source. We have a GitHub repository, which is listed here. These slides will be available, so you'll be able to get this link from the slides. If you're interested, you can go to GitHub. You can see the work that we're doing. We're continually updating this as we have ongoing work with AFRL to improve the build, to improve the quality of the proofs, and eventually we'll start to work on implementing more services. We've also published the work that just was presented here. We had a paper at Formal Methods 19 Industry Day. I'd be happy to give you a copy of that paper if you'd be interested in having it. We also have a paper that's been accepted to ERTS in Toulouse in January. It's a longer version of the paper that we submitted to Formal Methods 19. I can give you that as a preprint, but you can't distribute it, please. But if you're interested, I'd be happy to share those details with you. So thank you very much. I think I have maybe 5 minutes for questions.